Hello and welcome back. We start off with linear regression. We'll eventually get to artificial neural networks and subsequently convolutional neural networks. We'll start off by looking at this breast cancer data set that was taken from Kaggle, and the appropriate citation is given here, part of a scientific study. The idea here is to classify a certain breast cancer lesion as either it's benign or malignant. Okay, so which is basically the categories here. If you look, MMM is malignant, and of course, the other category is benign, which is B, not shown here in this snapshot of the data set. So the each of the columns that you see here would correspond to a so-called feature of the breast mass, and each row corresponds to that of a patient. Okay, so how are these so-called features computed? They are computed from a digitized image of a breast mass biopsy. It's called the fine needle aspirate, and what they describe are the characteristics of a cell nuclei present in an image. So you have the picture of the cell nuclei, and you measure these properties of the cell nuclei from the image, and you list them against every patient. Okay. Now, the idea is using these so-called measurements or features, you classify the breast cancer as either benign or as malignant. What is interesting, of course, is that these features are hand calculated by from the images of the biopsy tissue or biopsy breast cells. Okay, so this is one what you call category of data that you can use in linear regression, even though this actually we'll see later is probably not a good candidate for linear regression. Okay, so here there are the diagnosis is either M or B. So your target Y, as you call Y is your target, would be either 0 or 1, or you can even say -1 or +1. Okay, so -1 being benign or malignant, +1 being benign. Okay, so either or other way. So if you test positive, then yeah, you are you're malignant. If you test negative, you are benign. So -1 would be benign, +1 would be malignant. Okay, same thing for 0, 1. You assign benign and malignant accordingly. Okay, so that's your target. That's what you want to estimate whether a particular breast lesion mass that was found, maybe based on a test, is either benign or malignant. Okay, so this is one task that you can accomplish with this data, and this data we assume that all these features or some of these features have a direct bearing on this particular diagnosis of either benign or malignant. Okay. Another data set that is often used to illustrate linear regression is the housing price data set. Okay. Again, this is taken from Kaggle challenge, so you can go online, search for this data set, and there are quite a few versions of it, it seems like. Right? So the idea here is to predict the sale price of a house given some of its features. Okay, so these features could be continuous values, like for instance lot area, or it could be categorical variables like features like lot config. So it's a mixture of categorical and continuous features, and these features you use to predict the sale price of a house, and this is a classical linear regression problem. Okay, so let's just come back to get to what you mean by linear regression, right? So the idea is, we given some feature values, we should be able to predict the price of a, for instance, in the case of what we saw earlier for the housing price challenge, is given some features, we should be able to estimate the price of the house. Okay, so the price of the house is what we call the target here that you want to estimate Y. So, and X are the features. Okay, so what is this f of X that we have written there that gives you this Y? Okay, so this function f is the function of features, that X. So if X is a vector of features, like we saw, every house has a row corresponding to the table I showed you. So the X is a vector of features, and we give that as input to this function X, and its output would be one scalar variable, which is the price of the house. So that's the kind of problems we will typically look at in linear regression, wherein the input is a vector of features and we call it X, and the output is a scalar value Y. Okay, so then you might say, well, what is this f of X that we are trying to estimate? So for instance, In this case, I have plotted the first floor square footage and on the x-axis, first floor square footage on the x-axis, and the y-axis is basically the price of the house. Okay, the sale price of the house. So what we have is this very nice scatter plot. Okay, and so and it sees that there seems to be like a linear correlation, right? Almost between the first floor square footage and the price. So as the first floor square footage increases, the sales price also seem to increase. Now, if we draw a line through this, like this, okay. Now, this kind of captures the trend in this plot. So, if for a particular value of the square footage, you can kind of read off the value of the price of the house. So, for this thing, you can read off right here. So, this red line here, this is what I call f of x. Okay. So, in this case, I am considering only one variable, and x in this case is also a scalar, and output y is also a scalar. Okay, and it passes through the origin. So y equal to some constant times x would be the answer to this. Would be the solution for this line, right? So so the idea is now, as I hope it's clear, is to estimate this line, the equation of this line. This is what we refer to by f of x here. Now in 2D, it's like this. On the other hand, if you have multiple dimensions, you are just trying to estimate a hyperplane, right? In multiple dimensions, you're going to estimate a hyperplane. Okay. So if you have, let's say, if you are thinking of two features and you're trying to estimate a price, then you're just doing a plane, right? But if you have multiple features, here you have tens of features we saw for housing price prediction, and so you're trying to do this linear regression, which basically estimates a hyperplane. So if you just have one feature, so you're just trying to estimate a straight line. You have multiple features, then you're trying to estimate a hyperplane. Okay. So what is the simplest linear model that can relate y to x? In the sense, how do we estimate y as a function of x, and what you want to find that f of x, and we need to model that f of x. So we need a model for f of x, because we can only make a best guess. We don't have access to information that will tell you exactly what f of x is. Only these correlated features and the target, right? So the simplest model that can relate y to x is given by a model which is linear in x. This is given by this expression: y is w transpose x. Okay. So you might be put off by this notation, but you have seen some weird version of this in your school, right? When you're trying to fit something to a straight line, so then you might have used some equations like y equal to ax plus b, right? So this a and b are nothing but components of w. Okay. So this x is just one. This is in one variable, right? X is one variable, y is on the scalar output. So if this is the equation of straight line, so this is more general form, wherein you have more than multiple dimensions, and then you just have a weight matrix. So this w is you can think of them as coefficients, or generally you can call them weights of your model. In this case, it's a linear model, linear in x, and you're trying to, and the linear regression problem is basically all about figuring out this w which will best fit this data. Okay, so we'll see what that means in the subsequent slides. So before we go any further, right? So we also want to look at what have in the case of classification, what is this, what kind of regression can we do? Okay, so let's just plot one. Okay, so one of the features in this breast cancer data set, it would be the mean radius of the cell. Okay, it's not visible, might not be visible to you, but it doesn't matter. So mean radius of the mass or the cells that we have measured under the microscope. So I'm just going to write that down here. I'm going to call this mean radius. And then the y-axis is basically benign or malignant. Okay, so we're going to say is 0 if it's benign, and it's 1 if it's malignant. So once again, so 0 if it's benign and 1 if it's malignant. And let's just do this simple rule that maybe based on whatever little I see here, 13 millimeters. Let's say here is use a different colors, maybe black. So 13 millimeters is where anything above 13 millimeters is malignant. Anything above 13 millimeters is malignant. Anything below 13 millimeters is benign. Okay, so we'll draw a bunch of points here just to illustrate this. Try to use some colors which you've not seen before. So let's just use some yellow here, right? So for instance, there's a bunch of points which are all less than 13, which is benign, and then there's a bunch of points here, maybe again here, right? Bunch of points here, which are malignant, right? So this is M for malignant, this is B for benign because it's below a certain thing, right? And we are going to use only one variable. Of course, you can always try more, but easier to illustrate. So what is this? How would you do this classification? Ideally, the function we want has to look like this, right? Anything less than 13, it should always consistently give 0. I'll put this as 1. And anything over 13, it should immediately jump and give you 1 as this. Okay? But this is your Heaviside function, as you call, right? Heaviside step function. So we are looking for a step function. So this is your f of x. This is what we want. And this is a classification problem. So for classification problems, we want some functions like this, to approximate functions like this. Here too, you can do similar analysis that I'm going to describe for linear regression, but then there could be some errors because of outliers. Okay, and that's why people generally don't use regression. The regression that I'm going to describe for solving this kind of problems, these are called classification problems, right? And the f of x that we want is this shape, right? Whenever your x hits 13 millimeter, you want its output to jump to 1. Whenever x is less than 13 millimeter, you want its output to be at 0. Okay, so this is a function that we want to have, f of x. So that gives you the outcome, that is the desired outcome. Okay, so just to reiterate, okay, the idea is that linear regression is a system that takes a vector x. So I'm going to say vector x because we usually have lots of features, not one feature, right? And it usually outputs a scalar y. So most of the problems you will run into, there will be one variable you will be predicting. Okay, one scalar you will be predicting. That's your y, that's your target as you call it. And your input can be a vector. Okay, it will have multiple features in it. Okay. Once again, the way to do that, so let's see if you have, if you have a bunch of features, the model that you would have is of this form, with W transpose X, where W belongs to Rn, basically it has n components and each for one feature value. Okay. So the elements of X, which I've been repeating, is called features, and W is always referred to as the weight matrix or the weight vector. Okay. And what does it signify? The weights are also known as the parameters of the model, and what they do is determine the relative importance of each of the features. So now you have an explainable model, quote unquote, because if the W for a corresponding X is very high, then you know for a fact that particular feature is contributing a lot to a certain the output. Okay, so this is why I've shown here in the example. Features for both the regression problem, housing price, as well as the breast cancer problem, where we have a bunch of numbers, which we call them vectors. And for housing price, actually it's mixed because it has both categorical as well as continuous values in your x. Okay, so linear regression proceeds as follows. All you have to do is predict y given x as input by calculating this W transpose x. Okay. Now, why we can do this provided we know W, okay? But actually we will not, right? That's what we want to estimate. We want to estimate the weights. So we need what is known as the training data or the design matrix, okay? So these are the examples, x vectors x in the form of a matrix, okay? Just like that table, if you look at this in an Excel table, it looks like a matrix, okay? So every row of that matrix corresponds to a data point. Every column of that matrix would correspond to a particular feature. Okay. So, and with this, if you have a bunch of such examples, using that, we can actually estimate this W. Because once we have W, then a new X comes in. You can always calculate W transpose X and predict Y. Okay. So then how do we estimate W? So that is the question. That is the core focus of the linear regression algorithm. So the way we go about estimating the weights is that we estimate the weight so that the prediction of the model is close to the ground truth. So what I mean by the ground truth is the training data. Okay. So training data is usually provided in pairs. So you have a bunch of, if you have a X, I'm going to use subscripts, but this is just to indicate each subscript indicates a data point, not the component of the vector X. So xi, comma yi. You will have these pairs. Let's say you have m such pairs. Okay. In all of these formulas, x is implicit and you not mentioned it. So we want to estimate, how do we estimate W? We would like to estimate W so that the output of the model, so y hat is the model output. Okay, which is you calculate as W transpose X, is close to your ground truth, or what comes with your training data as the target Y. Okay, so this particular notation is basically is called the mean square error. So you subtract for every case in your training data or examples, you predict your Y hat, subtract it from the real, or you subtract the real Y from it, square it, and you do that for every case in your, or every data point in your training data. You add them and then basically you estimate the average, because 1 over m will give you the average error. Okay, that's the mean square error. Okay, so once you estimate this error, you can use this somehow to adjust W, that we will see later in the form of gradient descent. But the idea is, how do we, when we estimate W, what is the criterion that we have to consider? W has to be estimated so that this error is minimized or very low. Okay, so this is just using the training data that is provided to us. Okay, so how do we estimate W, right? So we had this expression y minus y hat squared, right? The sum of squared, mean square error. Okay, so we want to minimize W. Now, like I said, implicit that I did not really indicate is, if you just look at the expression, it's actually y hat of x comma W comma y or minus y, sorry, squared is what we are looking at, right? So let me write this. I'll use a different. So, for instance, we are looking at y hat of x, comma W minus y, which is a ground truth square, the summation over all the m the examples 1 over m. Okay, so the y hat is implicit dependence on x and W. Okay, now we are trying to estimate W. Okay, and how do we estimate W? So we know that we have to minimize this expression, minimize this error. Okay, minimize this error for a choice of W. Okay, so the easiest way to do that is to take the derivative of this loss function with respect to W and set it to 0 to obtain the minimum. Okay, when you do that, you get into a closed form expression, like you have an analytical expression for estimating W, which you can use. Okay, this is one way of solving the linear regression problem. We'll also see in some cases that we cannot, this is probably not the most efficient, and then we will then start using the so-called gradient descent algorithm, but this is the general idea. So we want to minimize the error between what we predict using the W's with our model W transpose X and the correct output Y. Okay, so if we do the sum of squares, an average sum of squares or mean square error, we want to reduce that. And we want to reduce that with respect to, by twiddling with the parameters W or the weights W. And the way to do that, of course, in mathematics is to set the loss, this is called the loss function or the cost function, and we take the derivative of this with respect to W, set it to 0, or the gradient with respect to W and set it to 0. And then once we do that, we can actually obtain an analytical expression for W. So if we do the math, then we end up with this particular expression for W, and these are known as the normal equations. Okay, and of course I remember that X, W and all matrices or vectors, but there's also in some cases a bias term making it an affine function. Okay, So y is w transpose x plus b. In case you're wondering where that came from, so for instance, if you consider usual regression, you can, for instance, think about a bunch of points. You fit a straight line through it, so you can fit a line which goes through the origin. Okay, here for this line b equal to 0, but you can also fit a line, for instance, which is a more appropriate, maybe something like this. Here b is some value. Okay, b is some value, so this is intercept. Okay. So x equal to 0, that's what this is. So this is the most general model. It's in one one variable, it's easy to illustrate. Okay. So using this form, you can actually estimate W given your training data set. Okay. But this is probably not the most efficient way when you have very large data sets or when you are trying to do real-time estimation. Okay. So we are trying to minimize this error. Okay. And what is this error? This is called the training error because this is done on, this is capital X that I'm typically using. This is done on the training data, right? The example data that was given to us. We used to do this. So this is called the training error. Okay. So when an unseen set of X applies, so X test comes in, wherein this is data you have not used for this process, is given as input, we would still like the error to be low. Okay. So, so the idea is the following: we need low training error, and we also want that on unseen data, that is the testing error, should be comparable to the training error. Okay, so this is where two important things arise. One is called overfitting. Other one is called underfitting. See, overfitting is when we have extremely low training error. Okay, and we'll see at some point in next two lectures where that comes from. So extremely low training error, but then when the new data set comes in, the testing and training error are not close. They are so far apart. Testing error is much higher than the training error. Okay, the underfitting is when the training error is larger. Okay, and it is large because your model is not good enough. Maybe a linear model is not good enough to fit the data. Okay, so then your training error would be large, and that's called underfitting. Okay, so typically, if you go to the point where we talk about deep neural networks, overfitting will be more common. Now, so we were talking about training error and test error and how it will be great if they are very close to each other, right? So typically test error will always be slightly higher than the training error, depending on the model, because not all models quote unquote generalize well. Generalization is when when new data comes in, your model performs as well as it did on the training data. Okay. Now, one of the steps that you can take to decrease the gap between your training and test error is to inject some prior knowledge about the model. You better inject some prior knowledge into the model. Okay. So there are many ways of doing that. So one way is, the most naive way is to use more complicated models. Okay. So for instance, we are talking about linear regression where our model is linear by itself, is linear in the variables, right, in the features. But we can have polynomial models. Okay, polynomial models which are more complicated. In that case also, the fitting will be very good. So your training error will be very small. Okay, but then overfitting can happen. Okay. However, we can provide some prior knowledge about what are our expectation. So one of the things we can do is, for instance, add this kind of a term to the loss function. Here W transpose W is sometimes that you will see in this form, W squared. Okay, the sum of squared values of your parameters of your model, or in this case weights of your model. So what this term does, since we are reducing the mean square error, in general we will try to minimize the sum. Okay, and but what this particular thing does is, since you have W squared, there is incentive for W to become small, for a lot of the W's to become small. Okay, so you want not only do you want this linear model, but forces the weights to low values. Okay, especially by tweaking the value of lambda. So for instance, you think that some weights values are too high and so it's not stable, then you just make lambda large enough and you try to solve for it, and in that way you will force the W's to be very small. Okay, so basically what you're trying to do is to select a particular type of solution. By regularization, you are forcing the algorithm to select a particular type of solution. So, for instance, there are different sets of W's that might satisfy this equation. Okay, ideally, of course, because you typically have lots of problems with noise, etc. Okay, so we won't go into that in much detail, but if you look at this particular expression, by increasing lambda is what you're trying to do is making sure that this term is weighed very high in the loss function, or j of w is the loss function, or the error term, and by doing that you are forcing w to become very small. In fact, sometimes you can drive it to zero depending on the form of this regularization. Okay, so what it is forcing to do is to choose a solution for w wherein all the w's are very low values. Okay, so for a lot of problems this is typically used, especially when you actually don't have too much data. Okay, the number of weights will be very large compared to the number of data points, and at that time you have the choice is to have this kind of regularizer. Think of it as adding more equations when there is generally less equations than there are unknowns. Okay, so this is one way of so-called regularization of the model, which helps to decrease the gap between the training and the test error. Now, once again, you have the mean square error, y minus y hat squared, or y hat minus y squared plus lambda w transpose w. We can still take the derivative of the left hand of this expression with respect to w, set it to 0, and arrive at a closed form expression for x. Okay, so analytical expression still possible. Okay, it's still possible by even with adding this regularization term. Okay, there are different regularization terms, but each of them enforces some expectation on your solution. Okay, so now we come to these so-called hyperparameters, which are also an essential part of all these models. So we saw in the previous slides, this parameter lambda that we used, to weight the W transpose W term. By tweaking lambda, you can enforce either small values of W, right? So this lambda is referred to as a hyperparameter. Almost all machine learning models have some hyperparameter that you have to tune. Okay. Now, how do you tune this hyperparameter? How will you make it work? Okay. Now, you'll be tempted to say, I will, put different values of lambda, train my network, and then, of course, test it on test data. So that's typically not how it works. Okay. So what you have to do is take a separate partition of the data called validation data. Okay. And you would tune your hyperparameter using that validation data. So after training with different lambda, you will test it on some validation data which is different from the test data in order to tune your hyperparameters lambda. Once again, hyperparameters are there for pretty much a lot of the machine learning algorithms. Even neural networks have this, and this is just an indication of how so many of the concepts are common across these models. So this hyperparameter in this case is only one parameter lambda, but in so many networks, for instance, many machine learning methods, there could be more than one parameter. So you need to have a systematic way of evaluating a correct hyperparameter, and for that you would need the so-called validation data set. Okay, so you wouldn't tune your hyperparameters on a test set, but rather you would tune it on the validation data set. Now, linear regression can also be solved with the normal equations, right? This can be done. Okay. However, when the data set is very large, millions of data points, or when the learning has to be done in real time, like you are getting 1 point at a time and you want to estimate, keep estimating your weight matrix or weight vector, right? Then this our learning algorithm. So I would say that this solving this normal equations, amounts to some learning algorithm. But so then we have to change to a different algorithm when we are trying to do only a few bunch of points at a time, or even 1 point at a time. This is where we use gradient descent. Okay, so we are going to take a brief look at the gradient descent algorithm and how it can be used for learning W, the weights of your model. In this case, especially for a linear model. We'll see that in the next video. Thank you.